Okay, this is a quick overview on drawing, interpreting, describing and explaining graphs to show rate. The shape of a graph changes over time for any particular reaction because it gets slower and slower, because as the reaction progresses, the concentration of the reactants that you started with always decreases. So this reduces the frequency of collisions between particles, and so the reaction slows down. So if you've got reactants A and B, the red and blue, and they get together to make the product, the purple product, then really quickly the first product is made, but then it takes a long time to get more products until eventually the reaction stops. So if we use these little pictures to help us interpret the graph, at the beginning, 0 time, you've got no product, so you've just got the reactants. And then at 1 minute, if we divide our amount of product up, these drawings, we're only making 4 molecules, so we've divided our amount of product up into 4. So in the first minute, 1 product molecule is formed, and then if the rate of this reaction was the same, in the second minute you would form another molecule of product. So if this was a straight line, then your second product would be here at 2 minutes. But you can see that you've had to wait longer, the time has passed more for you to make that second molecule. And then if it was still going at the same rate here, so 1 minute we made 1, 2 minutes 2, 3 minutes you would make 3. So our second point would be here if it was a straight line graph. But you can see you've had to wait longer for that third molecule again. So the slope of the graph, so this is a steep slope, this is not as steep, this is even less steep. The slope of the graph shows the rate of the reaction. So about this point here, the arrow, I'm using the BoardWorks PowerPoints, this arrow should really be over here at about this point. You've got your 4 molecules of product, and then the reaction stopped because you've got no more reactants. So a steep line is a fast rate of reaction. You've made a lot of product in a short amount of time, and then the line gets less and less steep as the reaction slows down until eventually you get to a point where the reaction has stopped. So measuring the rate of reaction means measuring the rate of change over a period of time. So you have to measure 2 things when you're measuring the rate of reaction: the amount of a reactant or product and the amount over a period of time. So if we did this reaction, magnesium metal with hydrochloric acid, making magnesium chloride, salt and hydrogen gas, what could you measure as the amount of reactant? So you could measure the mass of magnesium as it got used up, as it disappeared, in grams of magnesium per minute, or because your hydrochloric acid is being used up too, and then the pH would be less acidic, so the pH would go up over a period of time. You could measure the amount of product that was formed, so the mass of magnesium chloride formed in grams per minute. These 2 things in reality would be difficult to measure because they would both be present at the same time. So when you're weighing it, it would be hard to know, are you weighing the magnesium or is it magnesium chloride? So magnesium and magnesium chloride would actually be difficult things to measure. You could just put a pH probe into the solution and measure the pH of the hydrochloric acid. That would work. But quite often, because the hydrogen produced is a gas, we could collect that hydrogen and measure the volume of the hydrogen, or we could measure the overall mass, and as hydrogen was produced, then the mass would go down totally. Or we could even, after we'd measured this, turn the mass loss into the mass of hydrogen that was actually produced in grams per minute and plot that as a graph. So if you were collecting your hydrogen, you would collect it in a syringe, so you'd push this right up to the beginning here, add your magnesium ribbon to your hydrochloric acid, and then as soon as the hydrogen gas started to form, it would push the syringe back. So as this filled up with hydrogen gas, it would push it back and you could measure the volume. So then we plot. So first minute it makes about 14, this is centimeters cubed, which is about a mil. It's a mil. It's about 14 mils of hydrogen gas formed in the first 1 minute. If this was at the same rate, then 14 lots, another 14 would be 28 in the second minute. So if it was going at the same rate, you should have a point up here, a straight line graph. You should have at 28 for 2 minutes would be the amount of hydrogen, but you can see we've made a lot less, so it's slowed down from here to here, and each of the divisions it's slowing down and slowing down. You're making less than you did in the same time, in the same 1 minute, than the previous amount did, until eventually you get here. So overall you've made 47 centimeters cubed of hydrogen, and it took 8 minutes to do that. So if you were describing the graph, you just describe what it looks like. So the gradient. So initially is a great word if you're describing something. You want at the beginning. The gradient is steep, so the rate's fast. Then the gradient is less steep, so the rate slows, and finally you've got a horizontal line, the reaction has stopped. So really the descriptions are the steepness of the graph. You're explaining why initially the concentration of your reactants is high, so the frequency of successful collisions is high, so the reaction rate's fast. Then the concentration of your reactants drops, so the frequency of collisions is lower, so the reaction slows. And finally there's no acid, so your reaction stops.